Hello students, the topic is traveling salesperson problem. So in this lecture I will tell you what is a traveling salesperson problem and how we can apply the dynamic programming to solve the traveling salesperson problem. So dynamic programming says that you have to try out all the possibilities and then pick the best one of that. So if we try all the possibilities, it will be too lengthy and we may face the time complexity. So how are we going to pick up the best one with in a short period of time? So here we will apply the brute force. And how are we going to apply the brute force using the dynamic programming to solve the traveling salesperson problem? We will discuss in detail in this lecture. So if you take a look at the problem, we are given a table. You can also draw a graph for it with 4 vertices as the distances are given. You can see that the diagonals are 0 as the self multiplication, or there is no distance of any point to itself. So 1 to 2 is 10, 1 to 3 15, and 1 to 4 is 20. These are basically the distances. 2 to 1 is 5, 2 to 3 is 9, 2 to 4 is 10, 3 to 1 is 6, 3 to 2 is 13, and 3 to 4 is 12. 4 to 1 is 8, 4 to 2 is 8, 4 to 3 is 9, and the diagonals are taken as 0. So this is a matrix and that table is given for it. Now how we are going to draw the different routes that a salesperson can take. So if I start from the vertex 1, if the salesperson starts at the vertex 1, then he can go to the route 2, to the 3 or 4. Now, if he is at the 2, then what are the other possibilities if started at 1? That are 3 and 4. If he is at the 3, what are the other possibilities? If he is at 1, that is 2 and 4. If the salesperson is at 4, if started at 1, what are the other possibilities? That are 2 and 3. So now if we come take this, which is the leftover, that is 4. In this the leftover in root is 3. Here the leftover root is 4. Here the leftover root is 2. Here the leftover root is 3, and here the leftover root is 2. So the salesperson is started at 1, he can take the route 1 2 3 4, 1 2 4 3, then 1 3 2 4, 1 3 4 2, 1 4 2 3, 1 4 3 2. So the salesperson, after reaching the last route, he has to return back to the first node, that is route 1 or the vertex 1. So we will draw here vertex 1 at every end, right? Now we will calculate the distance from every vertex to the other vertices. We will use the table given to us, this one. We will use these distances and mention them at the routes taken by the traveling salesperson. We will start solving it from the bottom. If he is at 4, the salesperson at 4, then the distance from the vertex 4 to the vertex 1 is, you can see, that is 8, right? So we will write 8 over here. Then we will go to the next route, that is, if he is at 3, what is the distance from 3 to 1? You can see that 3 to 1 is 6, so we have written 6 over here. Then we will go to the next vertex, that is 4. So if the salesperson is at the vertex 4, then what is the distance from the 4 to 1? That is 8, so we'll write 8 here. If the salesperson is at the vertex 2, then what is the distance from the vertex 2 to the 1? 2 to 1, that is 5, so we'll write 5 here. If the salesperson is at the vertex 3, what is the distance from vertex 3 to 1? 3 to 1, that is 6, so we'll write 6 here. If the salesperson is at the vertex 2 here, so what is the distance from the vertex 2 to 1? 2 to 1, that is 5, so we'll write 5 here. Now We will move up. If the salesperson is at the vertex 3, then what is the distance from 3 to 4? 3 to 4 is 12. So we are not going to write only 12 here. We will also add 8. We will also add the 8 into the distance, whatever is the distance from the vertex 3 to 4. So 12 plus 8, 20. If he is at the vertex 4, what is the distance from 4 to 3? That is 9. 9 plus 6, 15. If the salesperson is at the vertex 2, what is the distance from 2 to 4? That is 10. 10 plus 8, 18. If the salesperson is at the vertex 4, then what is the distance from vertex 4 to 2? That is 8. 8 plus 5, 13. If the salesperson is at the vertex 2, so what is the distance from 2 to 3? That is 9. 9 plus 6, 15. If salesperson is at 3 vertex, then what is the distance from 3 to 2? 13. 13 plus 5, 18. Now, we will now move up to the vertices 2, 3 and 4. So here there are two adjacent vertices to 2, that is 3 and 4, to 3 that is 2 and 4, and to 4 that is 2 and 3. But from here we will take the minimum values. Here you can see that if we are salesperson is at the vertex 2, then we will check the distance. What is the distance from 2 to 3? And we will add this 20 into it. So 2 to 3 is 9. 9 plus 20, 29. 2 to 4 is 10. 10 plus 15, 25. So 25 is minimum. We will take the minimum one. Then if the salesperson is at the vertex 3, then we will check what is the distance from 3 to 2. 3 to 2, that is 13. 13 plus 18, that gives us 31. 3 to 4, what is the distance? That is 12. 12 plus 13 is equal to 25. The minimum is 25, so we will take 25, right? If the salesperson is at the vertex 4, then what is the distance from 4 to 2? 4 to 2 is 8. 8 plus 15 is 23. If the salesperson is at the vertex 4, 4 to 3 distance is 9. 9 plus 18 is equal to 27. So 27 and 23, 23 is minimum. We will take 23. Now move up to the first vertex. The adjacent vertices are 2, 3 and 4. Check the distances 1 to 2, 1 to 3, 1 to 4 and take the minimum one from these two, as we have already double underlined them, highlighted them. So we'll take the minimum distances out of the both. So the distance from 1 to 2 is 10. 10 plus 25, that is 35. 1 to 3 distance is 15. 15 plus 25, 40. Distance from the vertex 1 to 4 is 20. 20 plus 23, 43. So 35, 40 and 43, the minimum one is 35. So we will take the minimum one, that is 35. Now we will discuss the formula. How can we find out using that formula by dynamic programming to calculate these costs, the minimum costs. So this is the formula. Distance I, this is the initial vertex from where we have started our first vertex. We should say the one vertex. J are the other adjacent vertices, right? Plus cost J, the adjacent vertices. S is the set of the vertices. We minus from the J, and J belongs to the set of the vertices. So this is the formula from which we can calculate the minimum cost for the salesperson problem using dynamic programming. So we will check that if we are not having no intermediate city and the set of vertices is null, we are not having any set of vertices, that is, we will calculate the cost 2 null and the 1 vertex, right? So the distance from 2 to 1 is, we will check from there. So 2 to 1 here is 5. We will write it 5 here. Again, if we are going to calculate the cost from 3 null 1, so the distance from 3 to 1 is, we will check here, 3 to 1 is 6. Again, the distance from 4 to 1 is If we check it here, 4 to 1 is 8. We can also check it from the table we are given above, but it would be much easier if we go to the all the roots by the roots taken by the salesperson. Now, if we are at the vertex 1, we are starting from the vertex 1. So, if we are having one intermediate city, so we will be just left over with the one node. So, if we calculate the cost from 2 to 3 here, and we are taking the intermediate node as 1, so 2 to 3 we will calculate the distance for it, and then we will, so 3 is the intermediate node. So first we will, if we you remember the formula is that you have to this you have to first calculate the distance 2 to 3 plus cost of 3 to 1, right? So if you are going to calculate this cost, you have to calculate the distance of 2 to 3 plus cost of 3 to 1. Intermediate node here is 3, right? So what was the distance from 2 to 3? You can check it from, go back. What is 2 to 3? You can check it here. 2 to 3, that is 9. What is the cost? 3 to 1, you can check, that is 6. So 15. If we are starting from the node 2, intermediate node is 4, and that node is root is 1. So distance from 2 to 4 and the cost from 4 to 1. So cost we are given here 4 to 1 is 8, and the distance from 2 to 4 was 10. So in the same manner you can see that we can calculate it for all the routes taken by the salesperson. If we are at the set of vertices only left is, that is 1, right, for the case of one intermediate city. If we are given with the two intermediate cities, so now you can see here the intermediate nodes are 2 here. Now first we were having 1, so here we will calculate the distance of 2 to 3 and the cost 3, 4, 1. So how are we going to calculate it? We will add these two, right? Got the point? So we will add these two. Here you can see that we have calculated this cost, so we will use this cost in the intermediate cities. If we are having two intermediate cities or the two intermediate nodes or roots or the vertices, so here we are having, we will, how we are going to solve it, that is 2 to distance of 2 to 3 and the cost of 3, 4, 1. So the distance we are taking from the table, right, and the cost we are taking from 3, 4, 1 from here, that is 20. So we have added it like this. Again we will go for the next one, that is 2 to 4 with the second intermediate, and then 4, 3 and 1, 25, and we will take the minimum one. This cost we have also taken from here, right, 4, 3, 1, and we have taken the minimum one. In the same manner we will try it for the next route, that is 3, and we will calculate it taking the cost from the previous one and take the minimum one, that is 25, right? Again we will go for the next route, that is 4, and we will try out the formula over here, make the calculations and take out the minimum one. So this is 23, 25, 25, right? So we will go back here. So we have taken this 25, 25 and 23. Remember, now we have taken the values by this roots taken by the salesperson, and then we calculated them by using the formula. This was the formula, right? These were the intermediate nodes. This was the initial vertex or the initial route from which the salesperson started. Then we added the cost into it, the intermediate node set of vertices minus intermediate nodes, and the intermediate nodes belongs to the set of vertices. So using this formula we find out the minimum costs, and this gives us the same result we calculated using this these routes taken by the salesperson when started at the initial route, that was 1, and ended returned back to the initial route 1. So this is how we can take the different decisions using the dynamic programming and solve the problem of traveling sales person.